In this class, we are going to talk about number 9, and it is called spectral decomposition. This idea, it can be a bit hard because it takes several weeks of linear algebra course to talk about this idea. It's related to something like a diagonalization and eigenvalue, eigenvector, a lot of space things, and but it is important because it will have applications in, for example, image compression. You know, sometimes the image size is too large and you want to make it smaller, and basically JPEG is one format that is doing a good job, and somehow the original format has much bigger size. And the other thing is what we call as PCA, and you can just Google that, and it is a way to extract the important information from a set of data. But we will go through that in the end, but not today. Okay. So it is important, but it requires some linear algebra background. But what I want to emphasize today is try to have a feeling of that. That will be good enough. Okay. So just try to have a feeling. That will be good enough, really. So first of all, I want to introduce a terminology which is super easy. It's called a symmetric. So a matrix A is symmetric if A and its transpose is the same. So this also emphasizes that A has to be a square matrix. It is n by n. And if you draw a diagonal line, the 45 degree, and then this one is going to be Aij is going to be equal to Aji. Okay, so they are symmetric along with this dashed line. So it is easy to recognize whether a matrix is symmetric or not. And there is a theory called spectral theory. And it says that every symmetric matrix has a nice decomposition as the following. It can be written as the following form. It is a summation of some numbers lambda I and a matrix pi, and range from I equal to I from 1 to q, some numbers. So it can be the sum of such pairs. So let me give you a better picture of this. Okay, so lambda is just a number. But the important thing is that pi is a projection. So later on, I will give you the graphical idea about this decomposition. Okay, so let's say this projection matrix onto a space. Let me call that as EI. It's just a space. So the idea is roughly saying, okay, A can be decomposed into the sum of these things, and each of them is a projection matrix, and it will project to different spaces. Okay, And somehow these spaces are orthogonal. They are orthogonal to each other. So you will have the following properties. Kind of ignore the first one. This is only for mathematical correctness. The sum of these projection metrics is equal to the identity. It basically just says that when you look at this, you did not lose everything. You will project to 1 part, 2 parts, 3 parts, but every components will be collected. But feel free to ignore that part. But the next 2 parts will be quite easy to understand. If I and j are not the same, so it means you are going to do the projection onto one space. Let me show you here. This is EI, and there is an orthogonal basis, with orthogonal space, which is EJ. So when you make the projection onto EJ and then make the projection onto EI, then you will fall back to the origin. That's what it means. So if you have PI and PJ multiply together, which means you do the projection twice, and the 2 projection matrices are according to a different space. So in the end, the vector will fall back to the origin, becomes 0. And on the other side, you also have a formula if PI and PI multiply together, which is PI squared, and it is equal to PI itself. And this is also easy, and that's why I asked you to look at the matrix like an action. Okay, so this is EI, and if you have a vector and then make the projection onto EI, and then you make the projection again, it is not going to change the location. If you do the projection twice, the effect is the same as you do the projection just once. Okay, so PI is equal to PI. So these 2 and these 3, just some conditions about these projection matrices. And now I'm going to give you the geometrical meaning of this decomposition. Okay, so whenever I say the spectral decomposition, it means this form. And this decomposition is actually unique, but that requires some theoretical background. All you need to know is such a decomposition exists, and for every symmetric matrix. So symmetric matrices are nice, are great. Okay, so here is an example, and I will tell you the meaning. Say A is a simple matrix. It is a diagonal matrix, looks like this, with a lot of zeros. And in this case, you can write it as 1 times this matrix and 2 times 0, 1, 0 and 3 times 0, 0, 1. If you examine the first matrix, for example, then you'll realize if you have a vector x, y, z multiplied by this 1, 0, 0 matrix, diagonal matrix, then it will become x, 0, 0. So you will see that this is actually a projection matrix onto the x-axis. And similarly, this is a projection onto the y-axis. And overall, when you have a vector v, and then you multiply by a, by direct calculation, you will see it is equal to x, 2y, and 3z. And this decomposition will tells you that this action can be replaced by several steps. So here is the details. When we supply a vector to A, and it will make the projection to the three spaces. The first one, you will do the projection onto X, and then you get the X coordinates, or the components corresponding to X. And then you can do the projection to Y, then you got another vector which is corresponding to the projection. Do the projection to Z, then you will get the Z projection. So that's a projection into three different spaces: x-axis, y-axis, and the z-axis. And after that, you have to multiply by the scatter. This one will multiply by 1. This one will multiply by 2. This one will multiply by 3. So you see these numbers actually comes from these numbers. So after that, you will get just one copy of Vx, and two copy of Vy, and three copy of Vz. And after that, you do the sum. You get A times V. And in fact, like this one is actually x0, 0, y0, 0, well, 0, y0, and 0, 0, z. And after doing the scaling individually and take the sum, that's the same effect as multiplying by a matrix A. So this should be simple enough, but you will feel like, okay, this is just a diagonal matrix. Why should we do this? It is much easier to look at this one, right? It is super easy to look at this one, but who cares about these kind of decomposition? So the thing is, other matrices can look ugly, but still it has a nice form, just like what we described here. So let me give you another example. Okay, so this one is a bit tedious in terms of number, but the effect is simple. Okay, so it is 1/3 on the diagonal, and negative 2/3 on the off diagonal. Okay, so at least it wouldn't look so obvious what it is doing for this matrix. But if I tell you, after some calculation, if I tell you that the spectral decomposition looks like 1 times something, some projection matrix, plus -1 times another projection matrix. Okay, and here is the numbers. Give me a second. Okay, so you can verify that basically the identity or the equality is true, right? This is correct. Well, no. Yeah, it is correct, right? So you might say it is just from ugly to uglier, right? But actually this one is a nice projection matrix. This is also a nice projection matrix. If you look at the structure like this, okay, this is the plane x plus y plus z equal to 0. Or to be more precise, let me write it as it is a space that collects all the vector x, y, z, and such that x plus y plus z is equal to 0. And on the other side, it has a normal vector. This normal vector is the span of the vector 1, 1, 1. And let me call that as u. Okay, so although it looks ugly, this one is actually the projection matrix onto the space V. You can check that. For example, you can multiply 1, 1, 1, it will go back to 0. And if you take any vector on here, for example, 1, minus 1, 0, and it will stay the same. Okay, so this is the projection matrix onto the plane V. And there is another one. This is a projection onto the space U. So you will notice that, okay, these two spaces, kind of like the coordinate system, you have the x coordinates and the y coordinates, and in order to know what is the coordinates, you just do the projection, right? You make the projection onto U and make the projection onto V, and then you will know where you are. So now you've got some numbers and some projection matrices, and it tells you quite well what is going on. So let's look at that. So if we have V and it is sent to A times V, then it is equivalent to say this V, you do the projection individually, and you got V, well, let me call that VV. That's a stupid notation, but still it is okay. And let me just call that Vx because it looks like the x coordinates. And projection U, you got Vy. It is the height. Vx is the width and the Vy is the height. And after that, you will see that the part of Vx will multiply by 1. So it stays the same. But somehow the height, the Vy, will be multiplied by minus 1. So it becomes minus Vy. And eventually, you take the sum again, and you come out with AV. So what happens is, if you have a vector, you have to partition the vector into two parts, which is Vx and plus Vy. And then afterward, the output is Vx minus Vy. So this is A times V, and it has the same projection onto x, but when you project to y, it becomes minus Vy. So overall, the same action, the whole action is the reflection. You see that the part on V will stay on V, but the part that is corresponding to U will be will mirrored to the other side. So this action is actually a reflection, although the matrix looks ugly. So the idea is really just telling you that every symmetric matrix can be partitioned into this nice form, and there are some corresponding terminology to this, but it really just try to let you know there is such a geometrical meaning of this matrix. Okay, so you will see that this is the space we mentioned before, and if you have a vector, if V is on the space U, then you will see that A times V is equal to minus V. Okay, and if you have a vector W, and after multiplying that, you will see that it is equal to A times W. Right, so A times W is equal to W, and A times V is equal to minus V. So it all follows the same behavior, which is A times a certain vector is equal to a certain number times the same vector. And whenever this case happens, we call this vector as an eigenvector. And we call this lambda as the eigenvalue. Okay, so the decomposition is telling you that you are able to find some eigenvalues, and then you are able to find some eigenvectors, and the eigenvectors will generate the eigenspaces. So this one, well, I don't have to do this, right? So basically this plane is the eigenspace of lambda equal to 1. Okay, it collects all the eigenvectors, or it's basically equal to E1. Well, never mind, forget about this, sorry. So the eigenspace is the set of vectors such that A times V is equal to lambda V for a given V. For a given lambda. So each lambda will have its eigenspace, and the eigenspace is also the space that we're making the projection onto. Okay, so that's the idea of eigenvector, eigenvalue, and eigenspace. There are just some terminologies. Okay. So like what I say, this can be a bit beyond your scope. Depends on your background. Well, if you are in mathematics and you don't know this, then I will kill you. But if you are in different fields, then yeah, feel free to talk to me. I'm always unbiased, right? And by the way, most of the students in mathematics, they took linear algebra with me when they are in the first year. So anyway, that's so just make sure that you have a feeling of that, and if possible, get some idea of the terminology. That would be good enough for this lecture. So let me move on to the programming part, and I hope that will be a bit easier. So I want to go back and keep back and forth and emphasize some idea about NumPy array. So one thing which is very important is about the axis. So if you do NumPy with this command, so arange means that I want an array which is ranging from 0 to this number. Okay, but somehow the last number is not included. So 0 to 29, that's what we want. And you can do reshape. And this reshape is very powerful. You can designate whatever whatever the shape that you want, as long as the size is correct. Okay, so for example, 30 is equal to 2 times 3 times 5. So you can make it becomes 2 times 3 times 5. And this becomes a 3-dimensional array. So this is somehow beyond the matrix and beyond the scope that we can understand. But it is not too weird if you do the array, right? You can create an array of an array and you can create an array of arrays, and which is 2-dimensional. And if you create an array of 2-dimensional arrays, then it will be a 3-dimensional array. But whatever, you can try the following: arr.shape. It will give you 2, 3, 5. There are some other attribute which is called n-dim, number of dimensions. And so in NumPy, this is called 1 dimension. This is called 1 dimension. This is called 1 dimension. So eventually, this particular case will have 3 dimensions or 3 axes. And there is also another attribute called size. And in this case, it is easy. It is just 30. And 30 is 2 times 3 times 5. Yeah. All right. And so I want to point out that in NumPy, there is a set of functions. It is called aggregate function. It is a collective term. So we call it as aggregate function. And aggregate means kind of combining a lot of things and make one thing. And so in Chinese, it means 类似聚集，把东西聚在一起的一个函数。Okay, but the idea is it takes some numbers and generate one number or some numbers. Okay, I did not say anything about this, but this example will tell you more about that. So if you have A is equal to 1, 2, 3, 4, 5, 6, then you can see A as an array of 2 dimensions, right? And what happens here is A has 2 dimensions or 2 axes, and these axes has its own range. This one can range from 0 to 1, and this one can range from 0 to 2. And each of this is called dimension, or is called axis. So you will see that the dimension occurs here, 0 to 1, 0 to 2, and you will get the feeling of what are the axes. So if you do a function, for example, you can take a.max. It will generate 6. It will generate number 6. And that's what I meant by aggregate function, because you take 6 numbers and you generate just one number, which is 6. But it depends on your purpose. Sometimes it will be useful to set up the axis. If you again do the max and do axis equal to 0, then you will see that, okay, this one is axis 0, this is axis 1. So if you set up the axis 0, then you will do the maxima with respect to the axis 0. Okay, and you will output 4, 5, 6. So for each column, you will find one maxima and one maxima. So overall, if you have an array in general, for this example, you have 3 dimensions or 3 axes, and then you can see that it has a range from 0 to 1, 0 to 2, and 0 to 4. Okay, and whenever you are doing something like arr.max, you can set up axis equal to 0 again, and in this case you will try to kill this one. By kill, I mean you will take the maxima over this axis and then just generate one number. So the output will have shape just 3 by 5. The 2 is disappeared, and because it will take the maximum. So there are other aggregate functions. I'll just write it here. Okay. You can do sum. My writing is terrible. Sum, and you can do maxima, minima, and there are something called argmax, argmin. And similar to sum, you can do min. Min means average. And yeah, pretty much these are some frequently used functions, and all of them has a similar feature. Once you set up the sum, set up the min, it means that you want to take the mean of a collection of numbers, and somehow what are the collections? It depends on you set up. If you don't set the axis, then it is the mean of the 6 numbers. If you set axis equal to 0, then it is the mean of each columns. So it depends on your setting, and you will generate different outputs.